So problem 42 corresponds to section 2.4.1, and the statement of the problem reads as follows. If you invest 1,500 today and withdraw 2,500 in 3 years, what interest rate was earned? So the information that we have from this statement implies that this is problem 42, and the present value is how much we invested. Initially was 1,500, and at the end the future value, what we got back, was 2,500, and that happened after 3 years, so n equals 3. The question is, what is the interest rate? So from the formulas that we know, we know that the future value is equal to the present value times 1 plus I to the number of periods. So 2,500 should be equal to 1,500 times 1 plus I to the 3. So if we manipulate this, this turns out to be 5 divided by 3 should be equal to 1 plus I to the 3, or the third root of 5 over 3 should be equal to 1 plus I. And when we solve for I, we have I is equal to the third root of 5 divided by 3 minus 1, or I is 18.563110%. Now we're going to continue with problem 53 on section 2.4.2. This is on page 100, and the problem reads: Ben deposits $5,000 now into an account that earns 7.5% interest compounded annually. He then deposits $1,000 per year at the end of the first and second years. How much will the account contain 10 years after the initial deposit? So from the problem statement, we can find that the interest rate is 7.5%, and the initial investment is 5,000. This is problem 53. The interest rate is 7.5%. It is convenient to make a diagram in this case, and we're going to have on year 0 we have $5,000, and then on year 1 and 2, at the end of the first and second years, we're going to make investments of $1,000 each, and that's years 1 and 2. And then continuing on years 3, 4, 5, 6, 7, 8, 9, and 10, we don't have any investment, but on the 10 period, we want to know how much money we will have available here. So we're trying to solve for a future value, and that future value can be computed in parts. First, there are $5,000 that are contributing here. Using the formula for future value, we have times 1.075 compounded 10 periods plus $1,000 contributing by compounding over 9 periods at 7.5%, plus another $1,000 that were received in the account on the second year, and therefore they have 8 years left to compound interest on 7.5% per year, and the total value of this account would be $14,005.87. The next problem we're going to solve is problem 64 on page 102, section 2.4.2.1. And the problem reads: if you borrow $40,000 at 9% annual compound interest and pay it back in 7 equal annual payments, what will be the size of each payment if the first payment occurs 1 year after borrowing the $40,000? So this is problem 64. And from the statement we know that the present value is 40,000. The interest rate is 9%, and the number of periods is 7. But now we're gonna pay it in 7 equal payments. So actually the question is, what's the value of the annuity? Because these are going to be back-to-back cash flows for 7 periods starting on the first year. So the question is, the annuity is equal, or the solution is, the annuity is equal to 40,000 times A given P for 9% and 7 periods. The formula, we have that formula, and the formula would translate with these parameters to 1.09 to the n, which is 7, times I, which is 0.09, all that divided by 1.09 to the 7 minus 1. So when we compute those operations, now A becomes $40,000 times 0.1986905, and the annuity is $7,947.62. That's how much we need to pay. Okay, so let me correct here. This should be in 40,000, not 4,000. And remember that if we can work these problems like this, it's because, as it's stated in the problem, the first payment happens, or the first payment of the annuity happens 1 period after the borrowing the money. So the diagram that represents this looks like this. We receive $40,000 at t equals 0, and then starting at 1 year of difference, we start making payments, 7 payments, 7 payments of $7,947.